Okay, welcome everyone. Good afternoon, and welcome to this afternoon's session, in which I'm going to be introducing you to the wondrous world of AI and quite specifically machine learning. Um, and I know this is going to be a very popular module, I think, because I know a lot of you in your applications talked about how you are very interested in machine learning, and I can see a lot of benefits and wanted to develop your skills. So it's quite a significant module that we've got within the program, and to be honest, it represents quite a significant portion of what we do within the Pencore team now. So actually, it's quite an important part of what we do. It never used to be the case, and it's only really in more recent years that we've pivoted more towards the sort of AI and machine learning side of things. But definitely, there's been a very clear sort of sea change in that. Alison, if you're here, which you are, I'm just going to ask. I'm just going to make you a co-host, just so that you can help. Let anybody in. Oh no, wrong person. Where are we? Make co-host. There we go. Just so you can help let people in. That'd be great. Oops, where are we going? Oh no, we don't want that. There we go. This is why I can't multitask, apparently. Hopefully you had a bit of a exposure to Sean's training this morning, where he was talking about using whole systems modeling, and the whole systems modeling module contains sort of two key approaches, one of which network analysis, which is a fantastic approach that Sean's got a lot of experience in, and you saw this morning a little bit of a example of some of the work that that our HSMA did last year on that, in terms of the people from Devon and Cornwall Police. And also we'll be introducing you to system dynamics as part of that module as well. But today, this afternoon, we're going to be starting our journeys on AI. Now, I'm sure you'll be pleased to hear that there's no code this afternoon. Okay, so we're going to take this very gently, and we're going to make sure that we first of all understand the key concepts of artificial intelligence and machine learning before we get into some of the meaty details. Not least because actually these days it's very easy to do this kind of stuff in Python, because there are fantastic packages that have been made available that take out a lot of the complexity and remove a lot of the barriers to doing this. And you'll come to see in later sessions that actually when you come to sort of fit or train a model, you can very often do that in a single line of code. The packages we use are doing a lot of the heavy lifting in the back end, and a lot of it is actually the art form of shaping up your data, getting your data in the way it needs to be, and then sort of designing your AI algorithm in order to best approximate what you're trying to do. Okay, so let's plow on. So let's first of all start talking about what is AI. So AI, as I'm sure you're aware, stands for artificial intelligence. And by AI, we mean some way in which we are simulating intelligence, or some aspects of intelligence, using machines. Okay. And AI has evolved a lot over the decades to mean different things. And it's a kind of all-encompassing term and probably 20 years ago, if you ask somebody what they meant by AI, it would be very different to what we think of it today. There was certainly traditionally always a push towards essentially trying to create machines that you could have conversations with, and that would understand you and would reason with you, and that's still part of AI, but actually in more recent times the real focus of AI has particularly gone on to some of the machine learning stuff, which is what we focus on a lot in this course. So the way in which we simulate intelligence can include lots of different sort of definitions. So it might be that it includes things like learning. So these are all things that we think of as being intelligence. So the ability to learn. So the way in which we can make decisions, for example, to classify things, to say this belongs to this classification, this group. And that's a really important part of machine learning, and something that you will be doing a lot in this course, and likely in your projects as well. There's also the aspects of reasoning. So if we think about intelligence, we also think about the way in which we can reason. We can apply logical rules in order to come to some form of conclusion. It might mean having coherent conversations, conversations that can be understood, and that you can respond to those conversations in an intelligent way. Or it might mean perception. So this is quite a big area that we don't really touch on in the HSMA course, but worth sort of flagging up. This idea that getting machines to kind of recognize image or speech recognition is a big thing in AI. Certainly in the last few years, of the meteoric rise of home-based personal assistants like, sort of Amazon Alexa and the Google Home thing and Apple's own one. I mean, this is a big thing, and actually, it turns out this stuff's really hard. It's really hard to do. So we don't really touch on this kind of stuff because it's less relevant typically for the sort of things that you're going to be doing. But it is worth being aware that this stuff exists, and also we often borrow a lot of the approaches that are used in perception, particularly things like image recognition and speech recognition, for the kinds of approaches that we want. So in the HSMA course, we're going to pretty much focus exclusively on the learning aspect of intelligence. So when we talk about AI in HSMA, we're predominantly referring to getting machines to learn in some way. And specifically, we're going to be looking in this module at trying to learn to simulate human decision making, and that's what machine learning is all about. And also in the natural language processing module, learning to try and identify patterns within natural language, within free text, to try and extract information from that text, and using AI-based techniques to do that. So those are the two sort of key things that we'll be looking at in this course: simulating human decision making, which is the machine learning aspect, which we are looking at, starting to look at today and throughout this module. And the natural language processing side of things, but not the natural language processing, and I'll come on to this more when we talk about natural language processing next week. The natural language processing itself incorporates aspects of speech recognition and trying to get a machine to form coherent sentences and things like that. We don't really focus on that aspect. It's more about trying to extract information, because again, that's the kind of stuff you're probably going to need. So let's talk about machine learning. So machine learning is basically a field within AI, which is predominantly focused on developing algorithms that enable machines to learn via experience and by being shown data. Okay, so we're trying to get machines to learn something, and they do that via being presented with data and by improving themselves over time and gaining learning by experience. Usually, the purpose of developing some sort of machine learning algorithm is to make some kind of prediction or classification. Those things are slightly different, which we'll come on to, given some kind of input data. And usually, you're building something like this in the kind of sectors you work in order to provide some kind of decision support to a human, and hopefully learning something about the sort of inherent and maybe unobvious patterns that are present within the data. Now, it's really important to kind of stress this point that when you're developing machine learning algorithms, you shouldn't be thinking of machines as trying to replace human decision making, usually, certainly for the sort of stuff you're doing. And instead, you should see them in the same way that the modeling methods that we show you, when we talk about discrete event simulation last week, we talked about them as being decision support tools. So they're not there to make the decision for you. They're there to provide some evidence that can be considered in the round by the people that need to make those decisions. And you view your sort of machine learning algorithms that you develop in much the same way. They're not typically there to replace human decision making. It's just to give them some more evidence, some more insight to allow them to make some sort of decision. Unless, of course, you are planning on building Skynet, in which case you want it nice and autonomous and evil and taking over the world. Okay, so let's talk about some of the real benefits of machine learning. One of the key benefits of developing a machine learning algorithm is it allows us in some way to automate stuff that's done by human beings that would otherwise consume time or money resource. Okay, so you're, as ever with this kind of stuff, you're trying to automate something in some way, replicate a human-based decision, and automate that to try and make things more efficient and improve that process. You might be trying to better understand the way in which these decisions are being made, or better understand the data, particularly in terms of identifying things that we find it difficult as humans to see, but which a machine can identify hidden patterns within data that might provide us with some really useful insight. And sort of coupled with that is the benefit of allowing the data that you have to be used to generate those kinds of insights. But, and it's really important to stress this, machine learning and AI more generally, certainly in more recent times, has kind of been held up as a bit of a panacea, something that solves all of the problems. And I've heard that talked about in the NHS, about how AI will solve everything. And it's really, really not the case. And it's not the case for many, many different reasons. It's a fantastic approach, but it is not the solution to everything. And part of the reason for that is that, and this first one is really, really important, that machines can and will get things wrong. Okay, they are by no means perfect, and the algorithms that we develop will have faults, and there will be things that they will, even an algorithm that we've tested extensively and we think this is a really good algorithm, it'll get stuff wrong. And so you need to be aware of that when you're deploying a machine learning algorithm and making decisions based on what that machine is saying. Coupled with that, there are also very often, particularly so all of you are from either health, social care, or policing settings. And I would argue those are some of the most dangerous sectors, in a way, to be using AI. They probably have some of the biggest potential benefits, but there's huge, huge dangers with this stuff, particularly around some of the ethical considerations and what happens when you get things wrong and what's the impact of getting things wrong. And in the next session of this module, which is going to be talking all about ethics in AI, we're going to look at some examples of that and see what happens and talk about what happens when this stuff goes wrong. And that's hugely important. And it's really important if you're going to be developing these skills and developing machine learning algorithms. We're basically going to be sending you off into the world with the ability to do some pretty powerful stuff that can have a massive impact on people's lives. And so it's really vital that you understand what the ethical considerations are and understand that these things aren't perfect and that things will go wrong. And when things go wrong, what the impact is going to be. And so it's really important. And that's why we've made the ethics in AI a core session. It's a compulsory thing. Before we start teaching you how to do it, you actually need to be aware of what happens when this stuff goes wrong. And also another sort of thing that's worth flagging up is very often you may end up with more questions than answers. And so you might develop an AI machine learning algorithm in order to sort of get some insight, and you actually may find that you know even less than you thought you did. It throws up more questions, but that can often be a benefit and allow you to explore things in different ways. Okay, so let's start talking about some of the terminology and some of the key concepts of machine learning. So we'll very often, when we develop a machine learning algorithm, we'll talk about how we want to basically teach a machine to make a prediction or a classification. We want it to predict something or classify something in some way. And what we mean by that is that we want to get the machine to predict an output, which is commonly referred to as a label, in machine learning. Okay, so this important terminology. A label is basically the output given a certain set of inputs. So from these inputs, can this machine predict the correct label, the correct output? And in machine learning terminology, our inputs are referred to as features. So let's think about some examples. So you might develop a machine learning algorithm to, for example, predict whether a patient has a certain condition or whether they can receive a certain treatment based on aspects of their health, demographics, time since onset of their condition, etc. And in fact, this is exactly what my colleague Mike, is doing, and colleague Kerry as well, working on this long-term piece of work called the Samuel Project, which is looking at using machine learning to try and support decision making in terms of delivering clot-busting treatment, thrombolysis in stroke. And there's lots of complications around when people can receive that treatment, because it needs to be delivered quickly from the point of onset, and there's certain other patients that aren't eligible, some that are, but when they are eligible and that treatment can be delivered, it can not only save their lives but completely change their lives. So it's a huge area that's really important. You might, for example, thinking of our policing colleagues, you might use machine learning to try and predict the likelihood of someone reoffending based on input features such as what their original crime was, or whether they served a custodial sentence, etc. So that's the sort of thing you could get a machine to try and learn. And you're probably reading that and already thinking back to what I've just said about some of those ethical considerations. It really goes through the heart of everything you do within machine learning. You might try some classification problems. So you might classify whether a particular image that the machine is presented with is the image of a flower, for example. It's a very commonly used training set in machine learning that tries to identify flowers. Or classify whether the text that a machine is being presented with is positive or negative in tone. And you'll be doing that in this course when we come on to the natural language processing stuff, and we look at sentiment analysis and basically using AI to try and predict whether a piece of text is positive or negative. What was the intention, what's the sentiment of that text in terms of the intention of the author? So let's just think about features. So we go back to features. So that, remember, our features are the kind of inputs. You can think of them as sort of column headers of aspects of our data records that we can provide input data for, and we get our machine essentially to predict an output, and that's the label. So imagine we've got this example here where we're going to build a machine learning algorithm to classify whether someone is a Pencordian or not. So here I've got 4 features. I've got whether or not they like programming, whether or not they have questionable fashion sense, their age, and their height in centimeters. And so those are our features that we would use to try and train our model to try and predict these labels, these outputs. So here we've got a 1 indicating someone is a Pencordian and a 0 indicating they're not. And the idea would be that you develop a machine learning algorithm such that if it was given this information about whether they like programming, whether they've got questionable fashion sense, etc., that it can try and accurately predict whether or not they're likely to be a Pencordian. So those are our kind of features. And within machine learning, the features aren't all treated equally, because clearly some things will be more important than others. And part of the important part of what the machine learning algorithm is trying to do is to weight the features in some way, to identify which ones are more important, which ones are less important, such that their kind of relative contribution to making a particular prediction of that label, in this case whether they're a Pencordian or not, can be assessed. And that allows us to identify which features are more important. And that in itself can be really insightful, because it allows us to kind of identify what are the important things in identifying what a Pencordian is. Well, that's probably not that important. But if we suddenly take that to trying to do some image recognition to identify whether something is cancer, and being able to identify the important features that can identify whether something is cancer or not, suddenly this becomes a lot more important. So let's study this table above here. So ones and zeros. So ones represent yes and zero represents no, simple sort of Boolean true and false. So looking at this table above, which features do you think would be most important for predicting if someone is a Pencordian?
Whether they like programming?
Yeah, I'd certainly say that's a good one. I'd certainly say that's a good one. Anything else?
Possibly their fashion sense.
Yeah, I'd agree with that too. So I will just point out this is completely fictional data, although maybe the features that are important aren't in some way. But yeah, if we look at this, so we look at the ones that are Pencordians compared to the ones that aren't. So here we've got a label of 1. So this is a Pencordian. They like programming and they have questionable fashion sense. This one isn't a Pencordian and doesn't like programming, so that might indicate that that might be important, but they do have questionable fashion sense. This one down here also likes programming, doesn't have questionable fashion sense, but again we've got a 1 here, so that indicates they are. So this is looking quite important. And then this one here, again, like the top one, we've got that they both like programming and have questionable fashion sense. And this one here, which isn't a Pencordian, doesn't have either of those things. So it does certainly seem as though there seems to be a strong relationship between liking programming and being a Pencordian, which is probably what we would expect, given so much of our stuff is programming based. And questionable fashion sense might apply to some of this as well, so that may be important. And it's likely that maybe height doesn't have such a quite an important role to play as and age. So at a first glance, we get some sense about which features might be most important in making a prediction. So there are, when we talk about learning in terms of machine learning, there's not just one type of learning. And there are basically 3 main types of learning that we refer to when we talk about machine learning and a machine learning algorithm. Probably one of the most commonly used, certainly for the stuff you'll be doing, is supervised learning. So supervised learning algorithms are basically ones in which we show the machine examples with the answer. Okay, and that's where the supervised bit comes from. So the machine has access to the inputs, but also the outputs. And this is known as a labeled data set. Remember, labels refer to outputs in machine learning. So a labeled data set means one in which we've got the answer. So this example here, that would be an example of a labeled data set where we've not only got the inputs, we've got the outputs as well. So it knows what the answer is for these particular examples. And the way in which it tries to learn in supervised learning is it gradually improves itself by getting better at getting from a given set of input values to the correct output. So it tries to say, okay, I'm starting to see patterns here. So it's probably going to hone in on the fact in this data that, okay, well, likes programming seems to be quite important in the same way you guys just did. You just did exactly the same thing. Remember, we're trying to simulate that kind of intelligence. So it's picking out that, okay, I'm learning likes programming seems to be quite an important feature in predicting that somebody is a Pencordian or not, because when they do seem to be a Pencordian, and when they don't seem to be a Pencordian, etc. And so we use those algorithms, supervised learning algorithms, where it can gradually get better because it knows what the answer is supposed to be for the examples you give it. And so it can gradually try and improve itself to say, how do I get, I know the answer is this, how do I get from these inputs to that output? And it can gradually improve itself until it says, okay, now I seem to be getting better and better, that if I get a new set of inputs, I seem to be getting much better at predicting what the output is going to be. Now, supervised learning problems tend to be either classification problems, where you're predicting some kind of discrete class, or regression problems. And we'll talk a bit more about that in a moment. Regression problems, basically where you're trying to predict a continuous value. So this is kind of most of the stuff that you'll be doing will be supervised learning, where you have examples of what the answers should be, and you give that to the machine, and the machine is trying to learn how to get from those set of example inputs to that output. We've also got, though, as you may imagine, if you've got supervised learning, we've also got something called unsupervised learning. And basically, unsupervised learning is the opposite, where you have algorithms, but they don't have access to any label data. So they don't know what the answers are, and that's usually because we don't know what the answers are either. Okay, so it's really useful where you're trying to basically get the machine to try and delve beneath the surface and try and find inherent patterns or structures within the data, like clustering similar data together or identifying data that seems to be anomalous. But you don't know what the answer is. You're just getting the machine to sort of go in and root around and see what it finds. And that's really useful because there will be lots of situations where we don't know what the right answer is. And so unsupervised learning can really help in those situations. We've also got this thing called reinforcement learning. Reinforcement learning has been around for quite a long time, but is gaining traction as a really almost the Swiss Army knife of AI, in terms of a lot of people postulating this stuff can pretty much do anything effectively in theory. And basically reinforcement learning is where you have algorithms that try things and then they either get rewarded or punished. And basically the machine gradually learns to do the stuff where they're getting rewarded and avoid the stuff where they're getting punished. And it mirrors what happens in ecology, where how animals learn, and a lot of animals are reinforcement learners, where they learn to do things where they get rewarded usually by food, and punished usually for not getting food, and they gradually learn to forage, for example, in places where they're getting more reward. And so that's a very common thing in ecology, and this kind of learning is really useful for trying things out and learning by doing. Now, we used to do, last year we did do a bit of teaching in reinforcement learning, but we found it was a little bit theoretical at this point. But if anybody is interested in that, I can link you up with Mike. Mike's got some sort of training materials, and we've also got the materials from last year, the videos from last year that you can check out too. There's some great stuff that's being done in the field of reinforcement learning. Mike's doing a lot of work looking at trying to use reinforcement learning algorithms to improve ambulance dispatch policy and things like that. So there's some really good stuff that's going on in this world. It's a real emerging field in AI. Just to add as well, so I said the three types. There is technically something called semi-supervised learning, which is a variant of supervised learning, in which we have label data for some examples, but not all. But I flagged that up just to let you know that it's there, but we won't be covering that in this course. Okay, so I've mentioned a couple times now these concepts of classification and regression. So it's worth just taking a moment just to make sure that we understand what we mean by this. So classification problems are basically ones where we're trying to predict to which class an example belongs. Okay, so the Pencordian example there, that was an example of a classification problem. We're trying to predict if they're a Pencordian or not a Pencordian. And classifications may be binary. Very often they are, in fact, where you've essentially got two classes. It's usually true or false. Are they this thing or not? Is this cancer or not? It's that kind of thing that you'll be doing a lot in machine learning. But you can have multi-class classifications where you've got more than two classes as well. You can also have multi-label classifications where, so usually you're just trying to predict one label, one output for each example. But you can have situations where you have more than one output that you're trying to predict for a single example. So let's think about some examples of these sort of combinations. So we might use machine learning to predict whether a patient has condition X or not, and that would be a binary classification style problem. We might use machine learning to try and predict which condition this patient has, which would be a kind of multi-class classification question where you're trying to predict, it could be one of many things, which one do we think it is? Or we could be saying, what are the multiple conditions this patient has? So, and that would be an example of multi-label classification, where for a given patient and their features, their inputs, what do we predict are the various conditions that they have? So there's more than one output, for an example. So that's classification problems, and most of the stuff you'll be doing, particularly in this course and probably for your projects, will likely fall into this camp. But there are also regression problems as well, and basically regression problems are ones in which we're trying to predict a continuous value. So rather than a classification, is it true or false? Is it this thing or that thing or that thing? We're trying to predict a continuous value, some sort of number, as the output. So often these outputs will represent the probability of something occurring, or we can use regression for things like, tracking house prices, predicting house price movements over time and things like that. So we might think about regression problems, things like, what's the probability that the patient can safely receive this treatment, or what's the probability this patient's about to be admitted to hospital, something like that. So that would be a kind of regression type problem. Okay. So before we go any further, let's take a pause, and I want to split you into your groups, and I want you to spend the next 15 minutes having a bit of a chat about some of this stuff and some ideas for how you think some of this machine learning could be used within your organizations or within your particular systems. And then when you come back, I'll ask a few groups to kind of share what they've talked about and think about, the different kinds of learning that we talked about, things like supervised learning, but predominantly, but also unsupervised learning. You can think of examples where that could be useful, or reinforcement learning, where that could be useful. So partly this is to get you to think about, some of this stuff and what this means in a real world context and how you might apply this. But also, you all need to be having sort of one eye now to what your projects might be. And this may help sort of stir up some project ideas that you could actually do for your HSMA project. Okay, so I'll split into your groups now. Just spend about 15 minutes having a chat about this, and then we'll come back and we'll find out what a few of you have been talking about. So don't forget to nominate someone just in case you are picked on, and I'll bounce around the chats and see what you're talking about. Okay, let me open up the rooms now. Hello everyone. Okay, so welcome back. So there were some good discussions going on. I managed to get around to a few of the groups and heard some really interesting discussions taking place. So just for the interest of time, I'm just going to pick on a couple groups just to sort of feedback some of the things you're talking about, so that everybody can hear. So of course it is, that can only mean it's time to spin the wheel of names. So let's bring it up. I'll shuffle it a few times. Make sure this is fair. And let's spin it. Yeah, I think that's going to be deep thought. Okay, somebody from deep thought. Do you want to just feedback briefly what you were sort of talking about? Some of the things you were chatting about.
Yeah, sure. So some of the things we were talking about, so within supervised learning, we were mentioning, for instance, risk stratification approaches. So where you know, based on past data, say where there might be higher propensity for emergency department admissions, or risk of developing, say, chronic kidney disease, and you could, for instance, use that to inform future volumes that might go into the system. Or for instance, for chronic kidney, the example we saw, if you could stratify people into levels of risk, you could pull them earlier into, say, a tertiary care setting before they develop chronic kidney disease. Richard in our group was also mentioning something, so in terms of features, something where you could use signatures as well, in terms of, say, speech when you call 999, and based on what you say, but also maybe signatures in your voice patterns that might help you inform or not whether that's a high priority for, say, a cardiac arrest or so. And then in unsupervised, I think what we were, for instance, giving as examples, you could use it for profiling. So if you have a lot of variables, but you're trying to define, say, 4 or 5 main groups to then consider interventions for, rather than just having one explanatory variable. So you're trying to say something, what service they access and what time of the day with which professional. You could try to create these groupings. But we were commenting that we felt it was most useful if you create these clusters and then go back to whether it's the clinician or the expert in logistics and kind of discuss like those clusters. And yeah, we didn't really get into much of reinforcement learning, but I suspect with some things like the pathways, that you could create these artificial pathways with a certain similar goal seek, say how fast you go through the system or so, and then iterate through the, yeah.
Brilliant. No, thank you. There's really good ideas that you've been discussing there. Really interesting as well. You talked about, sort of patterns in the voice. I mean, one of our HSMAs last year was looking at GP notes and trying to sort of unpick stuff from GP notes, and unfortunately fell over because mainly because of the very boring issue that it's very difficult to get the notes out because of system issues. But one of the things that started to explore in that project was whether basically, can you try and predict an imminent admission from GP notes? But it may not just be the kind of words that are being said, but sometimes just sort of meta stuff like, how are we seeing that the GP is suddenly writing more when they're talking about this patient? And that seems to be quite a good initial predictor of something happening. So yeah, really interesting looking at some of that stuff. Fantastic, great ideas. Okay, so I'll spin it once more. Let's hear from one more group. Shuffle it a few more times. And let's spin. Let's see what this lands on now. I think it's going to be, yeah, looks like it's going to be Max. Okay, so somebody from Max, you want to share what you've been talking about?
I don't mind. So I think we had a few chats about different things because some of us worked for the council, some of us work for the police. I work in mental health, so I'm a cognitive behavioural therapist. I spoke a bit about projects that I could possibly do about, we have people that obviously refer in wanting therapy, and they put a lot of data in on the referral form. So they put comments of what their main problem is and whether they're using drugs and alcohol, if they've had previous therapy. So something about, at the moment, we're having humans going in and reading that and deciding where they go. So whether that could speed up the process, because at the moment we've got a backlog of 100 people waiting to be screened. And that's obviously delaying their treatment. So whether if we could have some sort of, machine learning of reading that comment and identifying, I think we said it might be semi-structured because there's some things that we could guide it with, but there might be some things that actually it could find out from reading that. And then I was saying about how there is already a project. I don't know if people have heard of it. It's called IESO, so IESO. And if you're going for therapy in the NHS, you can either wait for face-to-face or video therapy, or we almost have like an agency worker system where you get put through to IESO for live chat therapy with another therapist. And all of the data from that is being used for deep learning. So you can Google it, they publish all their studies and stuff, but they're basically analysing thousands and thousands of therapy session scripts, like transcripts, and using that to learn about different types of depression. So they found there's like 8 different actual, within a depression kind of diagnosis, there's actually like different types that they found that respond better to different types of treatment. And they've also found, that the language that the therapist is using can also improve the outcomes for the patients as well. So there's all, and they've published it all. So whether that's interesting for people, that's something that's already happening, but not in the NHS. I think we were saying there's like ethical issues of us using that kind of data, but this is a private company who's doing that.
Yeah, no, that's really interesting. Thank you. I think the second one I hadn't come across that, and I think that sounds like that's kind of an unsupervised learning clustering type approach from what you're describing, which sounds like a really interesting use of that, where you're drilling down. I mean, because it's very clustering is very often used in sort of academia, where you can do things like cluster similar papers together and stuff like that. But where you're thinking about that and trying to cluster, okay, well, within depression, there are these groups that seem to cluster together, where you've got this kind of depression, and then these kind of people have these kind of common traits. So that's a really interesting use, actually, of
Fascinating. A bit
learning.
scary, because they want to have a robot therapist, basically, to perhaps replace my job in future. But,
that is quite scary. Okay. That's the issue with having the private company, I guess. But you could go out there and do something that's more of a decision support thing. I think certainly the first thing you're talking about as well, in kind of sort of reading through and getting through this backlog. I mean, that sounds like it's actually natural language processing, and in fact, I think you'll get a lot from the natural language processing stuff, which you could automate a lot of that information extraction very easily, and then maybe even combine it with a machine learning algorithm that would then try and sort of automatically identify and make predictions to ease that sort of triage process as well. So I think that could be really interesting. Brilliant, thank you very much. Excellent ideas sort of popping up there. Okay, so let's move on, so I'm already running over time. So let's talk about some more sort of important concepts when we come to do anything in machine learning, and these are sort of the fundamentals that you kind of need to know in order to be designing machine learning algorithms. So when we're trying to teach a machine, let's imagine we're talking about supervised learning now, because that's going to be most of what we talk about. We're trying to teach a machine to try and make a prediction using supervised learning, where it's got some example data, where it's got the answers, so we've got a labeled data set, and we're trying to teach the machine to get to these outputs given these inputs. The data that we present to it is known as the training set. Okay, so that's the bit of our data, the slice of our data that we're going to give to the machine, which has examples that it can learn from, and it has examples of, given these feature combinations, this is the associated label, i.e. the answer. But obviously, once the algorithm has learned, and when we come on to talk about neural networks later in the course, you'll see that these algorithms are usually very, very good at learning this stuff from training sets. We also need a way of checking how well it's actually picked up on this stuff, because obviously it's been given all the answers. So we need some way of being able to check its performance, and for that we provide it with a new set of data, which also has all of the inputs, the feature label, feature values, and the labels, the answers. But this is for data that it hasn't seen yet. And so it can then use that new data to see how well its learning will translate beyond the data in the training set. So in other words, how generalizable is the algorithm? Has it learned to be generalist? Can it take its learning from the examples that it's seen in the training set and apply it to new stuff? Because that's ultimately what you're trying to do. And so that new slice of data that you're giving it, that you've sort of held back to one side, is known as the test set. Okay, so we think about our data. We've got our labeled data set here. This is some data that's got a load of different examples, and for each example it's got the data for the features and the label data, and in other words the answer, the output, and then we take a slice of that labeled data set off, and we use that as training data, and the algorithm will use that to train itself up and try and work out what the inherent patterns are and gradually get better and better. And then when it's done, when we think it's at the stage where we're happy that it's trained sufficiently, we then test it out on a new slice of data from the same data set, but this is data it's never seen before, And then it can check itself to see how well it does. So given these sets of inputs, what prediction does it make and how well does that match up to the actual answer in the test set? Now, later in the course, particularly when we start talking about neural networks, you'll also hear us talk about validation sets. And validation sets are a little bit like test sets, but unlike a test set, which you basically hold back during the learning process, the algorithm does not see that test set until it's finished training. With a validation set, it does have access to it, and every now and then it can take a peek at the validation set to check how well it's doing. So it's training on the training set, but then it's sort of taking a peek every now and then at the validation set and saying, okay, how well am I doing on data that I'm not using for training? And then based on that, it can improve itself accordingly. And as I say, that differs to a test set, which it will only see once it's fully trained, or once we declare it to be fully trained. And these things are really commonly used in neural networks, and as I say, you'll see more examples of that when we come on to the neural network stuff, and particularly when we come on to the stuff in sentiment analysis as well, you'll see examples of that. So if we had our labeled data set and we had a train validation test split, we'd have a chunk of our data that we'd give to the algorithm to learn from. And then whilst it's doing that, it's taking a peek at the validation data every now and then to help it get better. So it's using these two things in combination, but in different ways. And then once it's finished training, it would then be tested on the test data to see how well it performs. Now, whenever you're trying to train a machine learning algorithm, we have to be very careful, well, about a number of things actually, but one of the key problems that you need to be aware of is a problem known as overfitting. And this is a really common issue in machine learning. Now, later in this module, you'll see examples, and Mike will talk about in his section about where you do want to deliberately overfit, and he'll explain why you do that, and at least initially. But overfitting is a problem. You don't want that an overfitted model to then be used out in the wild. So let's talk about what we mean by overfitting first. So let's look again at our table from earlier. So this is the table we had earlier, which has various features and labels to identify whether someone is a Pencordian or not. And we said that it looks like that likes programming in particular seems to be a pretty good predictor of whether somebody is a Pencordian. It seems to be if they do, they seem to be a Pencordian. If they don't like programming, they don't. And questionable fashion sense actually seems to be pretty good as well. Maybe not quite as good as likes programming, but seems to be quite highly weighted. So imagine that data from before was our training set. Now let's imagine we've trained our algorithm. Our algorithm has concluded that likes programming and has questionable fashion sense are sort of the highest weights. These are important features. Let's imagine now we give it some data that it hasn't seen before, and this is our test set. Let's have a look and see how well you think our learning has applied to the test set. So we said that likes programming was pretty much the most important thing. So this is data that it hasn't seen before. This one likes programming and has questionable fashion sense, so it's likely it's going to predict they're probably a Pencordian, but they're not, so you can get that one wrong. This one doesn't like programming, doesn't have questionable fashion sense, it'll probably predict they're not, and they'd be right on that occasion. This one doesn't like programming, so they're probably going to predict they're not. They do have questionable fashion sense, but they're likely to be predicting a no here, but they are actually a Pencordian. This one likes programming, doesn't have questionable fashion sense, but again, because this is really important, we'll probably take that, and it'll probably predict they are. They'd be right there. This one doesn't like programming, doesn't have questionable fashion sense, but is a Pencordian. So clearly, the patterns that we've learned within our testing set, within our training set, are not serving us well. What do you think's happened?
It was a really small training set, so we've we've overfitted the data.
Yeah, I mean, so I mean, obviously, in this example, it's an incredibly small data set, and you wouldn't ever train on something that small. But you're right, we've got a problem of overfitting, and basically, what's happened is we've learned things that are too unique to this slice of data. So this training data here, we've learned patterns that are in here that may not be representative of the data as a whole. They may just be quirks of this particular data. We've got too specific to the data in the training data. So in the training set above, this original one, we concluded that likes programming and questionable fashion sense were basically the most important features, and likes programming was probably the strongest. But from the test set, we can see that the importance of those features seem to be unique to the training set. And in fact, when we look at this wider test set, it doesn't seem that's that important, because in fact these features here seem to generate as many no, they're not a Pencordian, a 0, as they do a 1 where they are a Pencordian. So that would kind of, if this was our training set, we would no way have concluded these two things were the most important. So basically our training has become far too specific to the particular nuances of this training set, and that's known as an overfit. And it's known as an overfit because in machine learning, fitting is the term we use to describe training. Okay, so when we say we fit a model in machine learning, it means we've trained a model. So fitting is training. So an overfitted model is basically one we've trained too much. Okay, it's become overtrained and it's picked out stuff and it's become really good on this stuff. It's amazing on the training set. But the problem is that it's picked up stuff that's too unique to this training set. And because of that, it doesn't have that generalizability to be able to then take that outside of the training set to the wider world. And therefore, it's probably useless, because we don't build a machine learning algorithm to predict only stuff in a training set. There's no reason to do that. We already have the answers for that. We need it to use the training set to develop these general rules, general learning, so that when we present it with new cases where we don't have the answer, that it can predict the answer. That's the whole reason we're doing it. So if we get something that's overfitted, it's not going to do that, because it's picked up too much that's unique to the training set. So let's think about this in pictorial form. So if we consider this example where we've got two different classifications, we've got yeses and nos, ticks and crosses. Where would you say would be the true dividing line between those two different classes?
About 30.
Yeah, I'd agree with you. Around sort of here. It looks to be, as human beings, if we look at that, we can see there seems to be some sort of general division between this side and this side. Okay, so a model that's been trained or fitted well would probably identify that classification difference here. So we accept there's going to be a few outliers, but generally speaking, the stuff over here and the stuff over here, this seems to be the separation point. Okay, this is an example of a model that's been overfitted. Now, if this is our training data, imagine this is our training set. This is an example of what an overfitted model would do. It's got everything right here. Okay, so it's correctly classified. Everything on this side of the line is yes, and everything on that side of the line is no. We were to get 100% accuracy from that model when looking at the training set. But we can probably already see as human beings that unless we've got some very odd data, that's probably not going to be the shape of the true boundary between those things. And in fact, if we were then to look at the real data, the wider data, we then might find, well, there's more cases over here, and suddenly our accuracy is going to plummet, because all of the stuff on this side of the line is going to be considered a cross, and everything on this side of the line a tick, and it's going to get all sorts of stuff wrong. So clearly, this is a model that's been overfitted. It's become too tuned in to particular nuances that don't really represent. If we had all of the data in the world for this particular problem, it doesn't really represent where the kind of true dividing line is, and therefore isn't generalizable. Now, as well as overfitting, which is a very common problem that you need to be aware of, you also can have the problem of underfitting, and this is basically the opposite. So underfitting is basically where you haven't trained the model enough. It's undertrained, and it usually means the model is probably too simple. And that means your model is rubbish on not only the test set but also the training set. But because of that, it makes it easier to spot, because as it's training, we can see it's rubbish on that. It's not even picking up the training set stuff correctly. So this might be an example of we can see here where we have got a more sort of unusual fit, and this is actually the optimum fit that we would hope for, and an underfit might just say, oh, there's a dividing line here between these two groups, and that's clearly not enough. So that's a case where we haven't trained enough, or where the model is too simple, or probably a combination of the two, and therefore isn't able to identify what is actually the true differentiator between those two classes.
Sorry, Daniel, can I ask a question?
Yeah.
Is there chance of overfit or overfit or underfit influenced by the sample size? Should be more difficult to overfit with a larger sample size, I guess.
Theoretically, yes, although it depends on. So you obviously your training data, even if it's very, very large, is only ever going to be a small subset of all the true data ever. And remember, any data set is unless you have a very unique situation where you have a very finite sized data set for your true population. Any data set that you have is essentially just a sample, and so even a very big one is going to help, but it will be still a sample, and so you can still run into the problem of overfitting. But you're right. The more examples it has, the less you tend to run into that problem. But that also, if you've got a very large training set, that means you've likely got a very, very large sort of testing set and wider data that you want to apply it to, and so you still run into the same problems, just at a different scale. So it's still potentially a problem, and you can still get it'll still start picking up stuff that really doesn't exist, patterns that don't exist. Okay, so we're talking about quite a lot about how well a model performs, and so it's really important that we understand what we mean by that, and how we judge how good our algorithms are. And we can use various different metrics to basically work out how well our model has learned, depending on the kind of model that we've built. Now, the ones that we're going to look at just briefly now are for classifier models, but you'll see examples of other performance metrics both out in the wild and sort of mentioned elsewhere on the course. But these are the key ones that you need to be aware of when you're developing the kinds of machine learning algorithms that you're all likely to be doing if you're developing your own machine learning projects. So the first one is, and probably the most commonly referred to, is accuracy. So we often hear when people talk about machine learning algorithms, oh, it's got good accuracy, or it's got poor accuracy. And that's one of the most common things you'll hear in terms of how a machine learning model performs. So what we mean by accuracy is the percentage of predictions that the model is making correctly in the test set. So when we give it the test data, what percentage of them does it get right? So when it says something is true or false, when it says it's true, is it correct? When it says it's false, is it correct? And what percentage of time is it correct, basically, on the test set? So accuracy is calculated as the total number you get correct divided by the total number of predictions you make. So 100% accuracy basically means everything that you gave it in the test set, it correctly identified the correct output. And that's what a 100% accuracy would mean. So let's imagine an example here. So let's imagine these are the true values, these circles. Okay, so this is what our machine learning model is trying to predict. It's been given these circles, and it's trying to predict what color each circle is. So here it's predicted that it's green, which is correct. This one is predicted to be red, which is correct. These two it's got wrong though. So that one was red and that one was green. So obviously that's incorrect. But these three it got right: red, blue, and green. These two it got wrong. So that was blue and that was red. But this one it got correct here. So what would be the accuracy of these results?
%60.
Exactly. Yeah, 60%. It's got essentially, I've made it nice and easy. There's 10. I should have probably said that. So there's it got 6 out of 10 right. So it's 60% accurate. That's actually pretty rubbish for a machine learning algorithm. And you probably need to do some more work. That probably, if you got that in reality, you've probably underfitted your model, or it's too simple in some other way. Okay, so that's accuracy. And that's the one that everybody understands. And that's the one that people always talk about. But in doing so, they miss that there can be problems with just looking at accuracy, and we'll come on to that. But that's the main one that will that people will talk about when you talk about machine learning. The next one we talk about is precision. So precision essentially gives the percentage of correct predictions for a particular classification of interest out of the total number of times that classification was predicted, whether that was correctly or incorrectly. So it takes a little moment to sort of get your head around this. So imagine that we were saying, what's the precision of predicting a Pencordian, that somebody is a Pencordian? What we would do is we take the number of times, the number of true positives, the number of times that we said somebody was a Pencordian, and they were, we got it correct. And we divide that by the number of times that we said they were a Pencordian and were correct, added to the number of times that we said they were a Pencordian and they weren't. In other words, a false positive. We said something was something and it wasn't. We got it wrong. Okay. So whatever this thing is, so if it's a Pencordian, the number of times we said they were a Pencordian and were right, divide that by the total number of times we said something was a Pencordian, basically. And precision is really useful when your classes aren't evenly represented, because you may have a very small percentage of one particular class, which means your overall accuracy, even if you were rubbish at predicting that class, may be very good. But precision will allow you to say, well, yeah, but how good are we at predicting this particular class? How good are we at predicting that compared to, you know, the accuracy of overall getting everything right? You will find, for the sort of stuff that you will be doing, this is likely going to be a really important metric. Here, for example, we've got us exactly the same data we did before, and we know it's 60% accurate because we've got 6 out of 10 right. So that hasn't changed. What would be the precision in this case for classifying blue circles in this example?
66%.
Yep, 66%. That's absolutely right. So basically, we've got 2/3 of them right. Okay, so we're basically looking how many times did we say something was blue and it was. We said that one was blue and it was, and we said that one was blue and it was, divided by the total number of times we said something was blue. And so we said it was blue and got it right here in these two cases. We also said, though, that was blue and it wasn't. So in 2/3 of cases, we got it right. We said it was blue and it was. But in 1/3 of cases, we said it was blue and it wasn't. So the accuracy overall of this particular algorithm is quite poor. We're a little better at predicting blue circles than sort of overall accuracy. Then we come on to recall, which is sort of the flip side of that coin, really. So recall basically gives the percentage of correct predictions for the classification of interest out of the total number of examples that truly have that classification. So if we take our Pencordian example, if we wanted to assess the recall of whether somebody was a Pencordian, we take the number of times that we said they were a Pencordian and they were, and then we divide that by the total number of times we said they were a Pencordian and they were, but added to the number of times we said they weren't a Pencordian, but they actually were. So the ones we missed. And recall is all about stuff you miss. How much of the stuff did you miss by saying something wasn't something and it actually was. And again, recall is really useful when classes aren't evenly represented. So precision and recall are sort of two sides of the same coin, but allow us a really useful way to assess performance beyond just accuracy when we have, as you very often will, uneven class sizes. So if we were to take exactly the same data again, what would be the recall for classifying green circles in this example? Anyone?
Is it 50%?
Yeah, well, let's work it through. So let's think about the number of true positives. So the number of times that we said that something was a green circle when it was. So this one we said was a green circle when it was. This one we said was a green circle and it was. Okay. We take that, so we've got two examples there, and we divide that by the number of times we said something was a green circle and it was, so 2, plus the number of times we said something wasn't a green circle when it actually was. Okay, so in this case here, we said that was a green circle. Sorry, we said that wasn't a green circle, but it actually was. And we said that wasn't a green circle, but it actually was. Okay, so you're right, it would be 50% because we got it right. In two cases, we said something was a green circle and it was, but in another two cases, we missed these two green circles over here. Okay. It'll take a little while for that to sink in. And when you come to use these metrics in reality, it'll gradually, accuracy is easy because it's just the percentage of time you're right. Precision and recall can be a little bit more difficult, but if you think about recall in particular as being kind of identifying the stuff you've missed, that will help you think about that. So let's think about what these metrics would mean in reality. So imagine we're trying to build a classification model that determines whether someone has cancer or not. So if that model had very high accuracy, then that would tell us that the model is correctly diagnosing people as having or not having cancer most of the time, which is good. High precision of cancer diagnoses would mean that most of the time, when it says someone has cancer, they do have cancer. And it's very rarely telling someone they have cancer when they don't. And that's also going to be important. And a high recall would be the kind of flip side of that coin, would mean that when it's that it's basically picking up most cases of cancer, it's not missing much, and it's rarely saying that someone doesn't have cancer when actually they do. So given all this, can you think of a situation where a very high level of accuracy on its own might be very misleading?
Could it be the case that you have a condition that is rare? So most people do not have cancer, for example. So it could pick up every single case where people do not have a cancer and completely miss the 5% of cases where people do have cancer. So it'd still be 95% accurate, but actually not very good at all.
Yes, absolutely correct. So exactly that. This is one of the most common problems that you will likely run into when you're building a machine learning algorithm for the kinds of things that you're likely going to be looking at. So I will share with you the story of one of the HSMAs from last year who got very excited when he built his machine learning algorithm. I said, oh my God, it's 95% accurate. This is amazing. I'm so pleased with my model. Unfortunately, he had a situation, as many of you will, where the thing that you're trying to, this was where you're trying to predict hospital admissions. Now, obviously, most people at a GP surgery aren't, so trying to look at, basically if they're going to be admitted in the next couple of months. Most people aren't going to be admitted in the next couple of months. A very small percentage of people will. So what you'll fall into the trap of doing, if you're not very careful, is building a machine learning algorithm that, and basically what it learns is, I'll just say everybody won't, because that I'll be right 95% of the time. And that's essentially what it will learn to do. It'll just say, well, if I just say, no, they're not going to be admitted, 95% of the time I'll be right. But that's probably not going to be very useful, because it's not the 95% of the time that they're not admitted that you're really interested in. In fact, the whole reason you built it is to pick up that 5% of admissions. So you can have really high accuracy, but really poor precision and recall, because actually the classification of interest is terrible at. Because it's just saying everything is correct or not. And this is a very, very common problem that you will encounter. And we'll show you during the course ways in which you can mitigate against that, and things that you can do. But the most fundamental thing you can do is to make sure that you're not just talking about machine learning algorithms in terms of their accuracy, but also measuring their precision and recall. So if you take nothing else away, remember that, that don't just judge something based on its accuracy, because it's likely to be highly misleading, because a lot of the stuff you're going to be looking at, you're going to have a very small percentage of cases for the thing that you're interested in compared to the overall data. So just very quickly, I mean, I've sort of hammered this in, I think now, but imagine here, so this example that we looked at before, this dividing line at around 30 here would have a 93% accuracy, because 38 out of 41 were correctly classified. The only 3 it got wrong with these 3 crosses here. But so you might say, well, that's really good, really accurate model. But actually, when we look at the precision and recall, so how precisely are you getting yeses right, and what's the recall on no's, we find actually the story isn't quite as good. So I'd advise you sort of have a look back through these notes after the session, just to make sure you've got a good handle on accuracy, precision and recall, and make sure you know how to do those things. Okay, I've been talking long enough. It's time to move to the highlight of this afternoon, where we are going to have a bit of fun, and I'm going to set you off in your groups on an exercise in order to try and help me move to a desert island. You're going to use the skills that I've talked about this afternoon around all of the performance metrics and concepts of overfitting and features and labels. You're going to put all this into practice by trying to create your own little simple algorithm. So I'm going to get you in a moment to take a break before we start, so you'll have a chance to stretch your legs, but then you're going to come back and you're going to work in your groups. So here's the problem. Dan, having grown weary of the human race, has decided to relocate to a remote desert island, and to keep himself occupied, he's decided to pack a DVD player and a number of DVDs. And we won't worry too much about the fact that there are various logistical issues with how he's going to actually watch them. So what I'm going to do, after about 50 minutes, 45 minutes to 50 minutes-ish, I'm going to present you with a series of DVDs, a series of films. Now, your task is going to be to develop an algorithm such that when I give you that information in about 45 to 50 minutes, your algorithm will attempt to classify whether or not I take each of the DVDs listed to the desert island or not. Now, I enjoy a lot of films, and I've enjoyed a lot of rubbish as well, but I'm going to have to be really selective because I can only pack so much. So I only want to take the films that I love the most. So to help you develop your algorithm before you get this test data, you're going to be provided with some training data, which I'll give you in a moment. And this will be a list of films, and it'll say whether I decided they would make the cut as to whether I would take them to a desert island or not. So that will be your training data. Now, from that training data, you need to decide as a group which features you're going to incorporate into your training. So things like director, what the genre was, what year the film came out, etc. Use various online resources. IMDb is probably going to be good for most of this stuff, to get lots of information about the films, but I mean, Google will tell you most of this anyway these days. And just for simplicity, we'll just make for this exercise, all of the features should be Boolean. So you might have features that say, is the director Steven Spielberg, yes or no? Was the film released in the 60s, yes or no, etc. What you're going to do is your algorithm is going to give a score which will represent your weight to each feature, such that you give a score to a particular feature if that feature is true or false, or maybe if it's false, or you could use a negative score if you wanted. Don't worry, I'm going to show you an example in a moment. This will make much more sense. It probably sounds more complicated than it is. What you then do is you'd add up all the scores for the feature values for that film, and you'd have a threshold which you decide, which determines whether the film is predicted to be a desert island DVD. So let's show you what I mean. So this is an example. So you might decide that your features are going to be: was the film directed by Spielberg? Is the film from the 60s? Is the film a romantic comedy? So those are your features. And then these are your weights, your scores. So you're going to say, well, if the film is directed by Spielberg, I'm going to give it 100 points if it is. If the film is from the 60s, I'm going to give 400 points. If the film is not a romantic comedy, I'll give it 50 points. Okay. And then basically you can then look through each of these things and score them. So this top one, film 1, was directed by Spielberg, so we'll get 100 points. Wasn't from the 60s though, and it was a romantic comedy, so it's only going to get 100 points. And let's imagine we've decided our threshold is going to be 200 points. If we don't meet that threshold, we're going to say that film hasn't made the cut. It's not going to make it to the desert island. So what you're going to basically do is use the training set, the films I'm going to give you, to try and optimize and evolve your algorithm. You might want to consider carving out part of your training set to use as a validation set, and you could sort of peek at that every now and then and see how well you're getting on. Entirely up to you how you want to do that. What you should do though, as you're going through, is to consider these 3 metrics of accuracy, precision, and recall to monitor how well you're training and adjust your algorithm as you go along. So change the weights if you think certain things are more important. Does that help your training? Throwing out stuff that isn't important. If the genre doesn't seem very important, for example, chuck it out. Maybe you need to bring in some new features. They can be anything you like, as long as you can express them as a Boolean for this. You might want to change the threshold. Does that help you get better accuracy and precision and recall? But remember, be very wary about both overfitting, so getting too specific to the films that are given in the training data, and also underfitting, where you haven't learned enough. Okay, so I'll give you sort of 5 minutes to stretch your legs, and I'll post on Slack, on the Slack channel, the data, the training data, and then around sort of 4 o'clock, just before, I will post, and I'll let you know when it's done. I will post the test set. Now, I was originally going to get you all to swap your algorithms to make sure there was no cheating, but I'm not going to do that. I'm going to trust you. What I am going to do, though, is ask you to post, before I do that, before I give you the test set, to post your algorithms on the Slack channel. I'll explain how to do that. So make sure that you're recording your algorithm in some way. Once you get given the test set, you're basically going to apply your algorithm unchanged to see how well it works on the test set. So given these features and these scores for these particular yes/no answers, how well does that work on the test set, and how accurate and precise and how good is your recall on this? So you can't change it once you've got the test data. It's locked in from that point, and we'll find out who's got the best algorithm. Okay, so this is a bit of fun. I also, just as a disclaimer, have absolutely no idea if this is going to work. This is brand new for this year, never done this before. An important conclusion sometimes from machine learning is this data is not learnable with the data we have. So you might find the data is insufficient and you can't learn anything about my film viewing preferences, but I have chucked in enough there, I think, that you should be able to pick some stuff out. I've deliberately put certain things in there, so hopefully you will be able to. But regardless, the point of this exercise is to get you used to these concepts of features and overfitting and underfitting and weights, and having measuring accuracy and precision and recall and all of that stuff, test sets, training sets, is to get you used to doing this stuff by hand, so that when we come to actually show you how you do this in practice using Python, you'll be able to understand what essentially is going on under the bonnet and what all these things mean. Okay, so take about 5 minutes, stretch your legs. I'll open up the breakout rooms and I will post on Slack on the module 7 channel. So the channel for this module, I will post the training data. So have fun with this. I will bounce around the groups and see how you're getting on. Hi everyone. Okay, so I'm aware that most of you, if not all of you, have not quite finished because there was quite a bit of stuff to do there, and we overran a little bit earlier. So the first thing I'm going to do is suggest that if you haven't quite finished checking your algorithms, see if you can do that after the session or when you can, and when you do have an answer in terms of your metrics, how well your algorithm performed, then do post them in the module 7 channel on Slack, and I'll be fascinated to see how well you all got on. But I saw some fantastic discussions going on. I think the highlight of listening in was listening into a debate about whether Pulp Fiction was a romantic comedy, which I think will always be the most memorable thing I've ever heard in HSMA. So this exercise has certainly been entertaining, and hopefully you've found it really useful. And the great thing that I've seen is exactly what I hoped for, that you're all sort of looking at potential features and revising those features and revising the weights, and coming up with some ideas about the insights and using that to sort of iterate. All of this stuff you're going to be doing when you come to build the machine learning algorithms. It's just you won't have to be sort of doing everything from scratch and typing into Excel and things like that. But actually the process of refining and designing and building up your algorithms, you're going to go through very, very similar processes. So just before we close, did anybody manage to sort of assess the accuracy of their algorithm either in terms of the test accuracy or the training accuracy? Anybody wants to sort of share what they came up with?
So Deep Thought did.
Great. Okay, how did you do?
So we got accuracy of 69.4%, precision of 89.47%, and a recall of 65.38%.
Okay, that sounds pretty good actually, considering some of the things I've been looking at. And what sort of features were you using? What sort of the decade, the 1980s, were that was a strong predictive value. Yeah.
And then we also used whether the genre was sci-fi, mystery, or drama, and then we also used the 2010 decade as well. I think we were looking. We missed a few that probably would have benefited from perhaps another feature. Yeah, no, definitely. I think so. It's interesting you picked up on that. So there were, there's some things that are obviously you may have found that I was completely unaware of, because I've just genuinely put down my, the films I've seen. I've tried to list all the films I've watched. I probably would have watched pretty much all of them again, but certainly I was trying to just pick the best ones, and there were things I was unconscious of, but also things I was conscious of, and that's probably films from the 80s featured pretty strongly in there. I think sci-fi came up quite a lot in a lot of the discussions you were having, and that I'm aware that I probably like quite a lot of sci-fi films as well. If it's a sci-fi film from the 80s, probably even better. So yeah, I'm not surprised by that. Anybody else? Any other teams managed to get any results out?
So we got ours, I think. I don't know, because I don't know if we assessed it quite right on directors and things, but we've got 95% accuracy and 100% precision, but only 42% recall.
Oh, that's good. Those are good numbers. I think that's the best I've seen so far. That's very good. So
that's assuming I've done the Excel right.
Yes. What sort of features did you have in yours?
So we were looking at the genre. So we had like sci-fi, drama, and horror as getting a score of some points, with sci-fi getting the most. And then we looked at director, although we didn't actually use it in our scoring that much. I think we didn't necessarily know whether they would have got the score. We didn't get time to look. We had the two, if it was older than 2000, then it got some points as well. And we had negative points for remakes. But I think we didn't use that so much.
Yes, I deliberately threw in a few red herrings, like the remake of The Wicker Man and stuff in there, which yeah, so there were a few deliberate things I put in. There are also, I mean, so a few of you picked up on possible directors, so I deliberately put in a few of my favorite directors, being Christopher Nolan being one, and M. Night Shyamalan. So there were a few in there that were there that I sort of deliberately peppered in, but whether you could pick that out from the training data, of course, is another matter. Any other groups?
In the test or the training data, do you want?
Either or both, if you got them.
We only managed to test 11 of them, but we got in the training set, we got 85% accuracy, 88% precision, and 90% recall.
Oh,
and
wow, that's good.
In the 11 that we managed to test, we got 81% accuracy, 100% precision, and 75% recall.
That's very strong. So what features did you have?
We had, is it science fiction? Is it horror? Is it action, which was negative? Is it 80s? Does it involve time travel? Negative for Tarantino, positive for M. Night Shyamalan, positive for Hitchcock. And then we use IMDb ratings. And if it was less than 6.5, we had it as negative. And if it was over 8.3, we had a positive score.
Fantastic. So again, you know, some things that I hadn't considered. I certainly wasn't aware that, you know, about the IMDb score and any linkage there, but I know a number of groups sort of tested that out, and it seems there was some sort of relationship in there. So again, something unconsciously I like. Well done on picking up the time travel. That was something I deliberately put in because I do tend to like a lot of time travel films. So that was very deliberate. So well done on picking that up. That's great. I think that so far that might be the highest in terms of consistent results I'm hearing, but I'll be interested to see what people post on that when you finally get the score. Anyone else before we close off? No, great. Okay. Well, I hope that was fun. If you didn't manage to finish off checking out your algorithms, then do try and make some time after the session to have a look at that with your group and see how you came up, and do post your sort of final results up. Thank you for providing me with some insight into what films I like. I'm basically just using this as an extended way in which to get some Netflix recommendations, so thanks for that. But yeah, hopefully that was a bit of an insight, bit different, bit fun. It seemed to work in terms of what I wanted you to get from it, which you were all doing, which is fantastic. But hopefully it's given you a bit of a sort of introduction to machine learning, some of the core concepts within machine learning. And as you go on throughout this module, you'll see how to do this stuff and how to create some fantastic machine learning algorithms. And it was great to see so many of you falling into the same pitfalls that you will encounter when you actually come to build these things. It's good practice to think about these problems and how you overcome them. So fantastic. Well done, everyone. Thanks for coming along today. Hope you've had a good, enjoyable day. So no other sessions this week, but then next week, obviously, we start to get a little bit more intensive, and there are an increasing number of courses. So next week, we're going to be introducing you to, I can't remember, let me just have a look. I think we're doing, yeah, so next Tuesday in the morning, I'll be taking you through natural language processing, and I know a number of you are quite interested in that, and obviously a lot of parallels what we're doing there. So we're talking about words and how we work with words. In the afternoon, that will be a pre-recorded session, and I will post information. This is the introduction to geographic modeling. I will post out the links to that. You can choose, you'll be able to choose when you watch that. So obviously there's the time set aside for you to do that afternoon. But if you want to watch it at a separate time, that's not a problem. But do make sure you check that out, because there's some really good stuff in there, and we've had some great geographic modeling projects before. And then on Wednesday, I've got another full day. So in the morning, we'll be taking you through the advanced bit of discrete event simulation. So taking you through from last week where we did the SymPy stuff. I'll be showing you a bit more in SymPy and how to do it in object-oriented code. And then in the afternoon, we'll be talking about cellular automata, which is a really interesting area that neatly sort of introduces the concept of agent-based simulation and behavioral modeling. So hopefully lots of interest in that. But stay tuned, say, to Slack. The information you need and anything you need to install will be all posted on there, along with the materials, etc. you need to download. And once the sessions are up on YouTube from today, the recordings, I will post those, which will probably be tomorrow. Brilliant. Thank you very much for coming along today, and I look forward to seeing you all again next week. And I look forward to seeing what your results are of your algorithms. Well done, everyone. You did some really good work there, and have fun. And maybe go and watch a movie. You've got plenty of recommendations there. See you all. Bye-bye.